Think about typing a simple division problem into a calculator and watching the digits spill endlessly across the display. Divide 10 by 2, you get a clean 5. Divide 10 by 3, and the 3's push relentlessly off the screen. Decimals with a definite stop are terminating decimals. When digits continue without end, the number is non-terminating. These endless numbers are sorted into two distinct families based on their behavior. The first branch contains repeating decimals. In a fraction like 1/3, the digit 3 loops forever. That loop can involve an isolated block of several digits. Dividing 1 by 7 results in a sequence, 1, 4, 2, 8, 5, 7, that repeats in that exact order. These patterns appear, we call them rational numbers. Repeating decimals follow a set structure. The second branch contains non-repeating decimals. Have you ever tried to imagine a number that stretches on forever but never settles into a predictable pattern? These are called irrational numbers. They form a unique and complex category in mathematics, operating under a completely different set of rules than the numbers we use for basic counting. To see how they work, let's look at a normal or rational number. This diagram shows a box labeled rational, containing the fraction 1/2. It cleanly ends as the decimal 0.5. But irrational numbers behave differently. Watch as the symbol for pi breaks out of its box. Its decimal sequence, 3.14159, and so on, continues endlessly off the screen. If you cannot find a repeating loop in a non-terminating decimal, it is impossible to write that number as a simple fraction. The first strict rule of an irrational number is its format. This graphic shows the standard algebraic fraction, a over b. We place a large x over it because it is impossible to write an irrational number as a simple fraction where one whole number is divided by another. Instead, we identify them by looking at their decimal forms. An irrational decimal must follow two specific rules. It must never end, and it must never repeat a pattern. This can be tricky because some numbers go on forever but are still rational. This split screen compares the two. On the left, the fraction 1/3 converts to 0.3 repeating. A looping indicator shows it is predictable. On the right, pi's decimal sequence appears. Randomized colors and question marks highlight a total absence of any repeating pattern. Infinite length alone does not make a number irrational. It is the chaotic lack of repetition that defines it. Despite their chaotic nature, these numbers are absolutely essential for engineering, science, and measuring the physical world around us. For instance, this animated diagram shows a turning bicycle wheel. To accurately calculate the circumference and the total area of any circular object, pi is functionally required in the mathematical equations. Let's pause and test your understanding. Look at the number 0.818181. Based on the rules we've covered, is this rational or irrational? It's rational. Because you can identify the repeating 8-1 pattern, you know this number can be translated back into a fraction. To keep the rules clear, let's look at this Math Novice cheat sheet. The first bullet point states the primary rule. An irrational number cannot be written as a simple fraction, a over b. Next are the two rules for decimal behavior. An irrational number must have infinite decimals, and those decimals must never repeat. And finally, the reference points. The two most famous examples to anchor your memory are pi and the square root of 2. Keep practicing and refining your math skills. In the next lesson, we will combine these concepts into a larger category, real numbers. Mastering both rational and irrational numbers provides the complete foundation required to finally understand that full spectrum. Thank you for learning with Math Novas. Subscribe for more easy-to-understand mathematics lessons and continue your journey from basic math to advanced mathematics.